Let me tell you a couple things as we're getting started. First off, pinch yourself, make sure you're awake today. You really need to be present and active today. And I need for even those of us who are introverted to be honest and ask questions when you get confused and not 10 minutes after, because this stuff is foundational for the rest of the semester. It's also not something that you've usually had in any other class, so it'll take a minute to get into it, but we'll go slowly. So ask questions as many times as you want to, we can slow down. So the other thing is that on Wednesday after this class, I'm going to run over to the STEM Center. I think I haven't found a room yet, but if I can, I'm going to run over to the STEM Center, and I'm going to do a little workshop on the stuff that we're doing right now. It's a game where you can like move things around and actually like cement the stuff in your head. It's definitely not required. And I know that some of you guys have conflicts and can't make it, but here's what I want to ask for those of you who do come. Share the love with somebody who didn't, right? That's how you're going to say thank you to me for doing a little concept workshop. Cool? So that'll be after class on Wednesday. And then what happens a week from Wednesday? First test. Okay. And we'll finish this material pretty easily on Wednesday. We do all the hard stuff about it today. So I just have one little teeny tidbit to finish on the last set of notes, and then we'll actually get into action potentials and membrane potentials. Okay. So last time what we talked about is we basically took all of that cell stuff that you learned in 1610 and started to apply it to physiology by saying, okay, how does this correlate to how I work glucose or sodium or water at the intestine, right? And we called all of those epithelial transport. Does that sound familiar? Okay. But I would argue that filtration is also epithelial transport, because filtration is really moving things across an epithelial membrane, generally a capillary. That's an epithelial membrane, isn't it? But it doesn't depend on concentration gradient at all. It depends on a pressure gradient. But it's still going to be epithelial transport, right? So the primary locations for filtration in the body are wherever you have a pressure differential. Do you not have a pressure differential between the blood plasma and the interstitial fluid? Yeah? Which one's higher pressure? Plasma, exactly. So what's going to happen with filtration is it is not moving things from high concentration to low concentration. It actually doesn't care about concentration at all. It's moving things from high pressure to low pressure, yes? And primarily what it moves is water and any solute that is small enough to fit through the holes, yes? High pressure to low pressure. So a great example of filtration is making coffee. I realize we're in Utah, but you've seen it done, haven't you? Right? So you are going to have a membrane that's got holes in it, yes? And you're going to have high hydrostatic pressure where you pour the water in and low hydrostatic pressure here where there is zero or some water. And it's going to pull through water, yes, but also any solute that is small enough to fit through the holes. But it's not dependent on concentration gradient, because if there were grounds in the pot, would it still move through? Yeah, it would, right? And it's also not selective which thing is moving except by size. So if there was coffee, dirt, and red Kool-Aid in here, what would it pull through? Small particles of coffee, dirt, and red Kool-Aid. Yes, it would pull all of those through. Good? So it is not selective except by size. No ATP is required for transport. Now, at the site of transport, ultimately, of course, the heart created a pressure differential, but it's not like at the site of transport, right? And big things like proteins and whole cells should not move across. But let me ask you this. If you hooked up a fire hose behind a coffee filter, could you pull a bowling ball through? Yes, but only once. Yes? So if the pressure differential is really dramatic, like if a person has massive hypertension, can you end up getting, for instance, proteins in your urine? Can you get blood cells in your urine? Yes, because the pressure differential is so high that you actually kind of destroy the holes as you're going through. So filtration occurs at every single capillary in the body. That's actually where the interstitial fluid comes from, right? Blood plasma, okay? And it moves anything water soluble and small enough to fit through the holes into the interstitial fluid. Every capillary in the body collectively, except for the kidneys, filters out about 1 gallon per day But the kidneys are super duper good at it because of a couple of things. First of all, they're really porous, more holy, not but the other kind. So more holy. And in addition, there's a little tweak that actually ups the blood pressure really dramatically at the kidneys. So the kidneys, just your two kidneys, 47 gallons of filtration per day. You do not pee 47 gallons, even you weirdo that everybody doesn't want to take road trips with. No, you reabsorb the vast majority of that, but you do filter out about 47 gallons per day. Okay, so one of the primary things that the kidney is trying to do, not exclusively at all, is to get rid of water-soluble waste products, like for instance urea, right? Anybody remember where urea comes from? It's a byproduct of what metabolism?
Protein.
Yay, you're my favorite today. You're my favorite. Yes, protein metabolism. And so, of course, you have to have urea, right? Okay, so what would happen in a situation in which your kidneys were failing? What would start to happen to the concentration of urea in your bloodstream? It starts to increase, right? Okay, so what you can do in this situation is if your kidneys are failing you, you can fake it and do dialysis. So let me teach you how dialysis works, okay? Dialysis clears more than just urea from your system, but it does clear urea from your system. So let me explain to you how it works. So what dialysis is going to do is, in this person who has kidney failure, the urea concentration is increasing. And by the way, urea will screw up your pH, and then your proteins will start to be shaped weirdly. So what's going to happen is I have to cleanse the blood, but my kidneys aren't doing it, so I'm going to outsource it to a dialysis machine. And this is called hemodialysis, in which you actually take out the blood. There's other ways of doing it. And what you do is I'm going to take out blood, and I'm going to run the blood through this system. Inside the dialysis machine is a little disposable chamber. The ones that I've seen are about this big. I bet they're smaller now, though. And what happens inside this chamber is I have a super duper curved membrane, way more curved than this, but just so you can understand it. And then what I'm going to do is I'm going to run blood in, and then of course I need it, so I'm going to put it back in the body ultimately, right? Blood's going to go in and it's going to go back in the body, okay? Through this side, I'm going to run the blood, and this person has kidney failure, so tell me the concentration of urea on this side. High concentration of urea, okay? On this side, when I'm going to run counter current, because it actually is better for exchange, I'm going to run dialysis solution. I'm going to run it through, and the dialysis solution should have how much urea in it? None. No urea at all. 0 urea. And what this is going to do is it's going to allow for transport. If I make sure that this is low urea and this membrane is permeable to what? How am I going to get urea to move out? What does it need to be permeable to? If it's high here, low here. Yeah, I need it to be permeable to urea. And then what am I going to do with this solution? I'm not going to circulate it back in. I'm just going to dump it every time, right? Dump it into the trash and run fresh stuff through it. Does that make sense? So blood is moving in, my dirty blood, circulating back into the body. I'm running counter current and running dialysis solution by. And as that occurs, the urea is going to move from the bloodstream into the dialysis solution, then I'm going to dump it, okay? But this is not filtration because it's not pressure driven. It's what? What is this transport mechanism? High to low concentration through a permeable membrane. Just diffusion. It's just diffusion, right? Okay? Now, I don't just have to make the membrane permeable to urea. There's other things that you can clear out of the bloodstream. But if I don't want the volume of my blood and the volume of my cells to change, I better make it planktonic to blood plasma. I better make it isotonic to blood plasma. Does that make sense? So this is what you do when basically your filtration fails you. And if your kidneys are really, really failing, you can have to do this 8 to 10 hours a day, sometimes even 16 hours a day. In the early stages, sometimes you don't even have to go every day. You could go once a week, once every 2 weeks. Go ahead.
So they put in fresh, like, dialysis solution and remove it?
Yeah. Well, the dialysis solution is running continuously. Fresh stuff in, old stuff out, dumped down the drain.
Oh, so like...
Do you see? fresh dialysis solution always being run in, right? And then dumping the old stuff. Yeah, and you just get rid of the excess because the other stuff would have urea in it and it would screw up concentration gradient, right? Does that make sense? Okay, so that's how hemodialysis works. There's a couple other kinds of dialysis, peritoneal dialysis, in which you work with the peritoneal cavity. Okay, so that's filtration, and now we are ready to move on to membrane potentials. Okay, so we're going to start where we left off when we were building this, but you guys are going to help me build it, okay? And then we're going to change it. So here's where we were last time, and we said this, and we had already built it, but I want to make sure that you understand it. So I'm going to start out with just this. I'm going to start out with my concentration gradients for potassium and sodium, right? And are you guys comfortable with this now? You know these concentration gradients, okay? So potassium is relatively high on the inside compared to the outside, a ratio of about 30:1, okay? And sodium is relatively high on the outside compared to the inside, a ratio of about 15:1. So question for you. What is responsible for those concentration gradients? What is always working to keep them that way? Sodium-potassium pump to maintain homeostasis, the sodium-potassium pump. So let's put in our pump. And in order to maintain those concentration gradients, which direction is this pump going to pump sodium? Yes, sodium is going to go out. Potassium? In. And then 1 ATP for the pump every time. And this is all stuff we know, right? Everybody good on that? Okay, but working against us, and we haven't gotten to the point that we understand why it's there yet, but we will today, working against us is the fact that what also exists in the cell are leak channels for sodium. Which direction is sodium going to leak through that channel and why? Into the cell, why? High to low concentration gradient, okay? Now, again, to reinforce the stuff that you did before, why can't sodium leak directly through the the lipid portion of the plasma membrane? Charged, exactly. Okay, same thing here. This is a potassium leak channel. When given the opportunity, potassium is going to leak which direction? Out. Why? Concentration gradient, okay. All right, so now what we are going to do is we're going to introduce you to that same concept we did last time about accumulating a charge. So I want to make sure that you get this as we go through it. Okay, so let's just make sure we check in on your notes. So the cell membrane, in the absence of the cell membrane, could you have a concentration gradient? No, it's the barrier, right? It allows you to sequester one on one side and one on the other. We already know that the ICF concentration and the ECF concentration has high this, low this, but we need to add in a couple more things. So what I want you to understand is we're going to start out with not just positives on the inside and positives on the outside, but we also have some negatives, okay? And the negatives, the primary source of negative charges on in the intracellular fluid is a whole bunch of big negatively charged proteins, and they're big enough that they are not going to diffuse out, right? They're trapped. They would be structural and functional proteins like enzymes and that kind of stuff inside the cell, right? And they're trapped in there, always. And then the extracellular fluid also has negatives. The primary source of negative charges in the extracellular fluid is the high concentration of chloride ions, okay? So what I want to do now is talk about how we are actually going to get to what we call resting membrane potential. And then I've got an animation for you to reinforce it. Okay, so here's what I want you to imagine with me. Stick with me, and this is where you need to really understand what's going on because we're going to use this to change things later. So I want you to imagine the birth of a cell, okay? And the birth of a cell, what I'm going to do is I'm going to start out with something true and then add things into it. Really, this all happens simultaneously, but it's impossible for me to understand if I don't explain it sequentially, okay? So at the birth of the cell, I want you to imagine that the sodium-potassium pump immediately starts working to create those concentration gradients, right? So I have concentration gradients, birth of the cell, okay? So sodium potassium pump is working, concentration gradients exist. Then the next thing that I do is I add in the leak channels, okay, for sodium and potassium leak channels. You with me? Okay. And initially, what I want you to understand is before I start leaking anything, right before that, I want you to imagine the extracellular fluid has a net neutral charge, and the intracellular fluid has a net neutral charge. With me? Okay. Stick in the leak channels, close your eyes, let them leak for just a second. Initially, there is no charge to be contended with. They only leak due to their concentration gradients, initially, yes? And so, before there is any charge, which one is going to leak faster? Before there is any charge, which one's going to leak faster and why? Potassium, because it's 30 to 1. Also, I haven't told you this, but there are more potassium leak channels than there are sodium leak channels. So initially, potassium is going to leak faster, right, due to concentration gradient and the fact that they say it's more permeable to potassium, okay? So if I start out neutral, neutral, and this is the part that you have to get, neutral, neutral, stick in the leak channels, leak, but not at the same rate, yeah? Potassium is going to leak faster out than sodium leaks in. What kind of charge am I going to accumulate around the outside of the cell membrane? Yeah, positive charge. And what kind of charge am I going to reveal on the inside? Negative. Does everyone understand how I get that negative charge? Somebody asked a question. Go ahead.
Well, okay, so the positive is because the potassium is going faster out, right?
Mm-hmm.
But the negative, is it because of what's left in there?
Yes, exactly. They were always there, but every negative was masked by a positive,
Okay.
but I actually lost more positives than I replaced. So they're revealed, right? So that's why I always say that the positives accumulate on the outside, but the negatives are revealed. They were always in there, right? You just couldn't see them. Is that okay? Okay. Everybody good? Another question? No? Okay. So this happened almost instantaneously at the birth of the cell. Although I talked about them sequentially, they all happened almost just like that. And then this, both the concentration and the charge, is homeostatic for the cell. And I need to maintain it for the rest of the life of the cell. But what happens is that now that I have a charge, there are two motivations for each of those ions to move. Now that I have a charge, not only do I have to consider the concentration gradient for the ion, I also have to consider the charge for the ion. So I want you to think about this. A positive moving toward a negative, is it going to increase or decrease the speed? Positive moving toward a negative. Increase. Positive moving toward a positive, what's it going to do to the speed? Decrease. Okay, so now what I want you to know is that now one of these two ions, sodium or potassium, is going to speed up and be faster for the rest of the life of the cell at diffusing, and the other is going to slow down and be slower for the rest of the life of the cell. Which ion is going to speed up? Sodium. Yes? Because now concentration and charge are adding to one another. It's going to be really fast at diffusion. And why? Because sodium is a positive ion moving toward a negative. Okay? And what's going to happen to potassium? It's going to slow down. Yes, it's going to slow down because its concentration gradient is still wanting it to move, but it's moving toward a light charge, which is going to repel it, right? So now we can get back to the rate at which the sodium-potassium pump runs. So after you have established this is true for the rest of the life of the cell. It is homeostatic. You always have to replace it. So how fast does the sodium-potassium pump run? Every time it goes, it moves 3 potassiums because they're faster, diffusing out, and you have to balance it. It moves 2 potassiums because they slow down, yeah? And it uses 1 ATP for the pump. Got it? Okay. What was your question?
So that all happens before the sodium potassium pumps start?
No. So it all happens simultaneously. It's just so impossible, right, to figure it out. Doesn't the sodium potassium pump, so that's a good question. Where is the sodium potassium pump involved in this? Beginning, middle, or end? Yes. All of them, right? It was there to set up the concentration gradient. It needs to be there to maintain it. It is there at the end if you ever break it to fix it. So the sodium-potassium pump is always running, right? Is that okay? Are we good? Okay, question. No? No questions? Do you all understand how the charge got there? Because we're about to change it. We're going to change it in a bunch of different ways today, and you have to be able to figure out how the hell it got that way in the first place. No? Yes? No?
We'll just do a quick recap one more time.
Okay.
I'll ask.
Okay. I love it, Ruby. Okay, you ready?
Yes.
Okay. One more time. So it's all drawn in here. But let's just start out, again, birth of the cell. Imagine. Okay. Birth of the cell, little baby cell only has sodium-potassium pump. Right? Sodium-potassium pump is creating the concentration gradients for sodium and potassium. Yes? Okay. So we've got concentration gradients for sodium and potassium. No charge inside, no charge outside yet. Okay? Yes? Now I stick in what next? Leak channels. Stick in the leak channels. And before I have a charge to worry about, the only reason the ions will diffuse is concentration. So let them do that for just a second. It's instantaneous, guys. They will diffuse instantaneously. But in that instant in which they diffuse only due to concentration gradients, which one diffuses faster? Potassium initially diffuses faster than sodium because there's more potassium channels and a stronger concentration gradient, right? And when that occurs, instantaneously you will accumulate a what charge on the outside? Positive, and reveal a what charge on the inside? Negative, okay? Now you have charges to contend with, and one of those two ions is going to speed up when it's going toward its opposite charge. Which one? Sodium. And one is going to slow down when it's going toward its like charge. Potassium. Exactly. For the rest of the life of the cell, that is what's true. Because you are going to have this charge. This is homeostatic for the cell for the rest of its life. Not saying you don't change it, but you always need to put it back. So now, what is homeostatic for the cell is this, this, and this. Yeah? And so that's why that's working at that rate. Go ahead.
We get lost, like, so sodium is positive, right? So why is it going to speed up?
So it's not anything special about the sodium, it's the direction that it's going. Because sodium is a positive ion moving toward a negative inside of the cell.
Okay.
And opposites attract, right?
Yeah.
Okay. But potassium is a positive ion moving toward a positive outside.
Okay.
And the same charge repels.
Oh.
So it's going to slow down as a...
It's going to slow down, right? So after you have a charge, you have to consider the charge and the concentration simultaneously. Go ahead.
So the sodium will also speed up because the concentration gradient is lower for sodium than it is potassium?
The sodium-potassium pump, is that why it speeds up? Is that what you said?
So like since the ratio between the, if I'm understanding right.
That's fine.
So there's 1 potassium inside.
For 30 outside.
For 30.
Mm-hmm.
Okay. So for the sodium, there's 1 for 15.
Yes.
So since there's lower amount of sodium, is that why it also has this?
No. It goes down its concentration gradient and down its electrical gradient, but those add to one another instead of subtracting from one another, which is what potassium does, right? Because with potassium, what the concentration gradient is saying is, yeah, move out, but the charge is saying, get back in there. And so the collective effect is that it actually slows down potassium's diffusion rate, okay? But it's additive with sodium, right? The charge is saying come in, and the concentration is saying come in, right? And so it's collectively faster. Is that okay? Go ahead.
And then, just to clarify, we're saying potassium moves out first because it's a higher in the cell before we...
That's before you get
Right.
to the charge.
But it does that because we have 30 to 1.
Yes. Before you had a charge, concentration was all you had to deal with. But once you have a charge, you have to deal with electrochemical gradient.
Right.
And the electrochemical gradient is the combination of the charge. And by the way, there is a way to calculate which direction it's going to use. It's called the Nernst equation, but everybody hates it when I teach it. So I'll just teach it this way, and we'll run into the Nernst equation a little later, right? So what we have is at rest, after establishment of the resting membrane potential, after I have this, okay, the inside of the cell membrane is negative and the outside is positive. Okay, when I get here, this is homeostatic for the cell. This is homeostatic for the rest of the cell's life. We call this steady state or we call it resting membrane potential. This figure 710 in your textbook goes through exactly what I just did. It's impossible to understand in class, but if you look at it sequentially, it starts out with just concentrations, sticks in leak channels, accumulates a charge, impacts the charge, has the pump to balance it out. So it's really good as long as you look at it slowly. It's just not good to actually do in class. Okay, so what we have here is when resting membrane potential has achieved, we're in steady state, and we have both a concentration, an electrical gradient, we have an electrochemical gradient for the cell. Okay, so I'm going to show you guys an animation that reinforces what we just did. Okay. Her voice is really boring, but don't let yourself get bored, okay? Because this is important, especially for those visual people. Oh, wait, hold on. Boop, boop.
The human brain alone contains about 100 billion nerve cells, called neurons. A neuron, like every other cell, has positively and negatively charged ions, inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter.
Okay, let me show you what she's doing before she goes any further. So you can measure how different electrically the extracellular fluid and the intracellular fluid are from one another. If you stick a voltmeter in, here's how it works. It uses this fluid as the standard and measures how electrically different that one is. So the voltmeter will go in, hit this one first, which is positive, compare the second one to the first one, so the number is going to end up being negative, right? Because the inside is negative compared to the outside, which is the first fluid, and it measures about negative 70 millivolts, okay? Now, you don't have to know what a millivolt is because I'm not going to change the units later. You just have to be able to say, okay, that means that the inside is more negative than the outside with this measurement, and then we're going to start changing the number and sort of asking you to figure out what the hell's going on with it when we change the number. So this is called resting membrane potential, and it's about negative 70.
An intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at minus 90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to minus 70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.
Okay, so that gave you a little visual to work on, and then we'll reinforce it and start looking at the number now. So, what we said was after resting membrane potential has been established, meaning after you have this charge, potassium slows down, sodium speeds up, right? Due to the electrical gradient that I just created, okay? So the sodium-potassium pump is responsible now for, think, maintaining the concentration gradients, and isn't it actually responsible for maintaining the electrical gradients? Because it goes pump, concentration gradients, unequal concentration gradient gets you an electrical gradient. Yes? Okay, so what about the negatives? Why are we not talking about them? Because we can actually ignore them. It's lovely in phys when you can ignore anything. We can ignore the negative proteins because they're trapped in there, so they don't really like diffuse. The only way that you could get them in and out would be endo and exocytosis, and you don't do that on accident, right? How about the chloride? The chloride we get to ignore simply because now that it's established with the electrical gradient, it diffuses in because of its concentration and out because of its charge at about the same rate. So it's kind of like water in an isotonic solution, right? You can kind of ignore it because there's no net movement. So we get to ignore those. So now, all cell membranes are polarized. That's what we call this. And the polarized means negative, positive charge. So all cell membranes are polarized at rest. This is resting membrane potential. Now, is this cell actually restful at resting membrane potential? No, it's not. It's running that damn pump the whole time, right? But this is as resting as a cell actually gets. So all cell membranes are polarized and have what we call a transmembrane potential at rest, right? They have that membrane potential at rest. We know how it works. This number, minus 70, is an average. So neurons are about minus 70, and other cells are a little different, but it's always kind of like that, right? And again, the minus 70, just so you know, I use this fluid as the first one and compare how different that one is to it. It is polarized at about minus 70. So let's ask some questions. Okay. So now, do you see that since I'm working so hard and this is the way the cell is at rest, not only am I creating the motivation for sodium and potassium to move when I want them to, but do you see that I'm also creating what we call the transmembrane potential, the potential for things to move across the membrane for all ions? Yes? Right? Because the cell is charged. So positive ions are more attracted to the inside of the cell and negative ions are more attracted to the outside of the cell. So I'm doing something with sodium and potassium that can impact the movement of all ions. Okay? Okay. So together, basically, when I have charge and the concentration, it's the electrochemical gradient. All right. So now, what we're about to do is we're about to introduce the idea of electrical cells. So you guys have heard a million times that the nervous system is an electrical system and the muscular systems are electrical systems, right? You've heard this a million times. But no one ever really explains that very well until you get here. So now what I'm going to tell you is the nervous systems and the electrical systems are going to take this charged membrane. All cells have the charged membrane, but what's special about the nervous and the muscular systems is they are going to move charged things, ions, across the charged membrane to create a current. So in physiology, a current is something that's easier to understand than it is in physics. Did anybody else get really confused when they got to electricity and physics? I liked it when it's ballistics. I'm like, yeah, I get it. You're shooting a gun. I can figure out where it's going to land, right? Once I got to electricity, I'm like, I haven't memorized that equation. I don't know what the hell you're talking about. But in phys, when you create a current, you take a charged membrane, positive, negative, and you move a charged ion across it. If you move massive quantities of charged ions, you will create a huge current change. And that is, bringing this back to something you might give a crap about, that is how you cause an action potential in a neuron. That's how you stimulate a muscle contraction in a cardiac muscle or skeletal muscle or smooth muscle. So that's what a current actually is, the movement of an electrical charge across a charged membrane. Okay, so now, this is resting membrane potential. Yes, this is at rest. Not very restful or very easy to understand. But now we're going to start changing it. Okay? So what we're going to do next is we are going to start talking about a graded potential. So stick with me for just a second. Okay, so a graded potential, every single cell in your body has a resting membrane potential that's pretty similar to this. Okay? But does it make conceptual sense to you that even if you can't predict how the number would change, that minus 70, that number could be changed if, in addition to all of the stuff you're doing at rest, you stick in some gated ion channels and open them? Can you imagine that that number might change? Yeah? Because I'm going to move something, right? Okay. So if I stick in gated ion channels and open them, the number would change. We're going to be able to predict how it's going to change in just a second. Or can you imagine that that number might be different if, for instance, I was completely depleted in potassium in my extracellular fluid? Super duper low potassium, like in a starvation condition, right? Or I had way too much sodium in my system. Would that number potentially change? Yeah, it would change, right? Because you're measuring how different the extracellular fluid and the intracellular fluid is. Why did I choose extracellular fluid? Where are you more likely to have an ion disturbance? Extracellular fluid, right? Because I ate too much or I didn't eat enough, right? Is that okay? Okay, so those situations in which you have too much or too little are pathophysiology conditions. We're going to cover them at the end of this set of notes once you really, really get the normal physiology. But the other ones in which I stick in gated ion channels and open or close them are normal physiology conditions. And they occur in every cell. So these are all, this is just leak channels that we've been talking about thus far. The leak channels are always open, they're always doing their thing. But what if I want more sodium in, or less sodium in, or more potassium, or calcium, or something? I will stick in a gated channel. A gated channel? So, what we are going to do is we're going to start to talk about depolarization and hyperpolarization. So let's look at this graph for just a second and sort of figure out what the hell we're talking about. Okay, so minus 70 is blank membrane potential, resting membrane potential. But now what I'm going to do is I'm going to change from there. And the way I'm going to change first is I'm going to create what's called a graded potential or a local potential. A graded membrane potential or a local potential. And if I depolarize, if polarized is minus 70, that's how different it is. If I depolarize and make the intracellular fluid and the extracellular fluid more similar to one another, what's going to happen to the number? Closer to zero, because not polarized would be 0. Can we agree? Not polarized would be 0? Okay. So if I depolarize, I'm going to go closer to 0. But if I hyperpolarize, what would happen to the number? It's going to, give me an example of a number. Negative 100, negative 90, whatever. It's going to go the other way. Okay. So now I'm going to sit here and think about this for a second and be quiet because I don't, for those of you who get it really quickly, let the other people struggle for a second before you tell them. Okay. Because the struggle is the learning phase, sorry. But I want to figure out how to depolarize and how to hyperpolarize. Okay, so I'm going to give you guys two choices. Depolarize, right? Bring the number closer to 0. Which one will do it? Stick in and open a gated sodium channel or stick in and open a gated potassium channel. Which one will depolarize? Think, process, try to figure it out. Gated sodium or gated potassium will depolarize. Gated sodium or gated potassium. You have to stare at it, figure out which direction something would move, figure out what it would do to the number. What do you think? Anybody want to try to explain it? Go ahead.
Would it be sodium because you're going more to the positive?
Yeah, it's sodium, but it's nothing magic about sodium. It's that, stick with me, positive outside, negative inside. If I open a channel and I bring more positives from the positive outside to the negative inside, are the inside and the outside more similar, depolarized, or more different, hyperpolarized?
Depolarized.
Yeah, it's depolarized, right? Okay. Same question, you know the answer, but I want you to be able to process through it. Okay. How would I, from resting membrane potential, hyperpolarize? Open a gated sodium channel or open a gated potassium channel? I know you can do it by process of elimination, but I also want you to be able to do it by logic.
It's moving out, right?
Gated doesn't mean anything about the direction. Gated just means I can open it or close it, right? Yeah. The direction is still based on the electrochemical gradient. Okay. So what was the, okay, do you want to try to explain it, Taylor?
make the extracellular fluid more positive, or would it make the intracellular fluid more negative?
Exactly. So what I'm going to do is I'm going to take a positive from the already negative inside, making it more negative, adding it to the already positive outside, making it more positive. So that is not depolarizing, right? It's hyperpolarizing. Yes? Is that okay? Got it? No? Don't got it? Okay. Depolarize, hyperpolarize. Okay. So let's look at your notes. Depolarization, a reduction in the membrane potential, meaning moving closer towards zero. The inside and the outside become more similar in charge. This occurs when gated sodium channels, for instance, open and sodium rushes inside the cell. The membrane potential moves from -70 closer to zero. Yes? And by the way, you can even overshoot zero. It's okay. Don't worry about it. Hyperpolarization, on the other hand, is an increase in membrane potential, meaning that you go further away from zero, right? Start at -70, go further away from zero to -90 or -100. This occurs usually when a gated potassium channel opens and potassium rushes outside the cell, right? The inside of the cell membrane becomes more negative and the outside becomes more positive than at rest. So the membrane potential goes below -70. And then let's talk about repolarization for just a second, and then I'm going to do, I think, pair share with you guys. So repolarization, the repolarization is, okay, so one of the things that we'll learn today is massive depolarization is actually relatively common in neurons and muscle cells. So they do a massive depolarization. And you guys told me that depolarization was usually what ion channel? Gated sodium. And hyperpolarization was usually gated potassium. Okay, so I'm going to have a massive depolarization taking the number all the way up towards zero or past it, right? And I want to really, really quickly get that to -70. So what's the fastest way that I could get back to -70? Yeah, close sodium and open potassium, and all of those positives will go the opposite direction. But of course, that's going to leave all of my ions in the wrong place, but we know how to fix that, don't we? Sodium, potassium pump. So depolarize really quickly with sodium, repolarize really quickly with potassium, put everything back where it came from with the pump. Good? Okay, so I want you guys to try to think, pair share question. You can do it, just think through yourself and then go talk to somebody. If you're not talking after you've thought it through, you're doing it wrong. There it is. Okay, you can blow that up if you need it to use it. You can still do it. After you've read it through, talk it through. And if you get it really quickly, that's great, but you have to explain what happens with the other ones. Okay, go ahead and talk it through, please. Promise you one of them right. This is where kids start getting. I'm sure you guys help. Five more people. 3 more. Okay, ready? Brilliant friends. What is the answer? What do you think? The answer is A. All right. This gives us a good opportunity to reinforce something important, doesn't it? Okay, so anybody who got it correct and thinks they know why, brave enough, be supportive to try to explain it. Okay, I will be supportive. I'll get you if she doesn't get it. Okay.
So I guess my thought process is, if the sodium gated channels are open, it's moving towards 0. So it's
So explain the right answer first.
Okay.
The right answer is A.
Yeah, so I guess if it stops working, well, kind of what I was getting at is if the sodium pump, it goes towards 0. So it's depolarizing.
Mm-hmm.
But then we'd have to open up the potassium channels for it to go back down, so it'd have to repolarize. If it stops working, then it would just be, it wouldn't go up or down.
Okay, do you want to start, James?
Okay, so if the sodium potassium pump stops working, you have nothing pumping in and out of the cell, it would just diffuse into a neutral 0.
So in the absence of the sodium potassium pump, what happens to these concentration gradients?
Stay the same.
Meh. And if you don't have the concentration gradients, what happens to the electrical gradient? Meh. No electrical gradient either. So the order, to reinforce what we were thinking here, is the pump creates the concentration gradients. Concentration gradients are responsible for the electrical gradient. Does that make sense? Yes? Because that's what we said. That's how we said we got there, right? Pump creates the concentration gradients, and then the unequal leaking of sodium and potassium creates the electrical gradient. But in the absence of a concentration gradient, you don't have unequal leaking. Does that make sense? Unequal leaking? Okay, so let's reinforce the other ones. Okay, so anybody think they might know what would happen at B? If I add more potassium leak channels, what would happen to the number? Yeah, hyperpolarized, yes. Hyperpolarized, let more potassium out than I did normally, right? It's going to hyperpolarize. You got it? Okay. What about D, closing gated sodium channels? What does that do? Huh? It doesn't really do very much. It just stops depolarization, right? If I was depolarizing and then I closed them, I would stop depolarizing, right? Okay. So in this figure right here, let's just reinforce with this figure. You said this is resting membrane potential. Depolarization is sodium channels. How do I get repolarization? Close sodium and then open potassium, right? How do I get hyperpolarization? Open potassium from resting, right? Open potassium from resting. And then what about C? Increasing the concentration of extracellular glucose. Does this do anything? No. Complete distractor. Stop trying to distract me, Melanie. I had a harder one there, and then I thought, oh, it's nice to just like do something, and we're just like, she is BSing us. And she was. She totally was. Okay, so you okay with this? Okay, we're going to reinforce it now as we go through. Okay, so let us, now what we are going to do is we're going to try to explain graded or local membrane potentials and action potentials. And they're all going to be related to this story that we have right here. Okay, and if you don't get it, if you didn't get what we did before, just stop me as I'm doing this, because now I'm going to start changing it. Okay, so this is at rest. This is without adding anything extra. Now, of course, I'm going to add some gated channels. I'm going to start opening and closing them. That's all. This is background. Okay? So, graded or local membrane potentials. These occur in every single cell that you have, because some of you understood that I said if you stick in a gated channel, an ion channel, and open it, it's going to change that number in some way, shape, or form. Yes? Now we're going to look at how it changes the number. So what's going to happen is this is going to occur in any cell anytime you open an ion channel. It's going to be really important in neurons and muscle cells. So let's start with a neuron, okay? Neurons are long cells, right? Most cells are microscopic in length and width, but a neuron, right? The axon of a neuron goes from the lumbar region of my spinal cord all the way down to my little toe, right? So that's not particularly impressive to me. I'm not very tall, but there are a hell of a lot taller people than me, and it goes to their toes, okay? So what I want you to understand is what's going to happen is, let's start with the neuron. You remember the basic parts of the neuron from anatomy? Cell body with dendrites, yes? Axon hillock is right here in front of Dana, yeah? Okay, this is the axon, all the way down to here. Axon terminals are down here, okay? So what's going to happen is I can have small changes over there that I won't feel all the way down there, okay? And these small changes are going to be like this one. So a graded or local membrane potential is a local flow of current, read ions moving across a charged membrane, that decreases in intensity when you get further away from the site. So here's what I want you to picture. I have on the cell body and the dendrites a bunch of gated ion channels, okay? I'm going to make them first gated sodium channels, yes? And specifically, because it's easier to picture, I want to make them ligand-gated sodium channels, yeah? So that I can pour a little bit of ligand and open a couple, or a boatload of ligand and open a whole bunch, right? Okay, the ligand that I'm going to use is acetylcholine. acetylcholine gated sodium channels. Okay, so what's going to happen is at that site where you see the stimulus, imagine that I dumped 10 molecules of acetylcholine and it opened 10 ligand gated sodium channels. And that was going to blank polarize the cell right there. What kind of polarization? Depolarize the cell, yes. Move closer towards zero because it was sodium, right? Okay, so they're called graded because if I measured right here, I would have a decent sized depolarization, but if I measured over here, I wouldn't have much of a depolarization. So it's kind of like dropping a pebble in a pond. Drop a pebble on one side of the pond and the waves are only around the pebble. Drop a freaking boulder and you can make the wave go all the way over to the other side of the pond. So it's stronger at the site, it's weaker further away from the site. So it's called local or graded. And the other thing about it is that it can be strong versus weak depending on how much stimulus you add. So the other thing about strong versus weak is here. Okay, so X right here, or stronger X. X, let's say, okay, 10 molecules of acetylcholine gets me a little bit of a depolarization because it opens 10 ligand-gated sodium channels. Okay, stronger X, 50 molecules of acetylcholine, right? Gets me a stronger depolarization. So these are called graded or local potentials, right? Change that dissipates as you move further away from it and can be strong versus weak depending on how much stimulus started it. Is that okay? Got that idea? Okay, so graded potentials also can be either depolarizing or hyperpolarizing. So I want you to look at those two real quick and say, okay, Y and Z. One of them is recorded in a cell as I open ligand-gated potassium channels. The other one is recorded in a cell as I open ligand-gated sodium channels. Which one is opening ligand-gated potassium channels? Y. And Z is opening ligand-gated sodium channels. Yes? So they can be depolarizing or hyperpolarizing. Okay, so now we're going to do a little labeling to make sure you can put all this together. So on this diagram, what you're going to do is try to make sure that the vocabulary fits with the concepts that you're starting to get. Okay, so on this diagram, sketch the membrane potential recorded in a cell as it begins at rest, resting membrane potential, and undergoes a hyperpolarizing graded potential. There's a lot of words, but it's actually not that crazy a concept. So first thing is, resting membrane potential tells me to start where? Minus 70. Okay, I'm going to ask you some questions. What kind of channels get me there? Yeah, leak channels get me to minus 70. Yes, leak channels? Good? Okay. Now, it says to undergo a hyperpolarizing graded potential. Help me figure out how to draw that. Down. What might the number go to from minus 70 to minus 90 or something, right? Okay. And then, questions. What kind of channel is that? Gated potassium, opening or closing? Yes. Open, gated, potassium channel. Okay. This is resting membrane potential. What do we call this one? What kind of a potential? Graded. That's a graded potential. Yes. Okay. Good? Okay. So let's, of course, do the opposite one to make sure we reinforce it. So on the next diagram, we are going to start at resting and then undergo a depolarizing graded potential. Okay, resting membrane potential, where is it? Minus 70. Same questions till they get annoying. That means you know them. What kind of channels are responsible for that? Leak. Okay, and then it says to undergo a depolarizing graded potential. Where does that go? Up, closer toward? Yes, let's say zero's up there. Okay, same questions you expect me to ask. What kind of channels are involved there? Open. What? Gated. Sodium. Okay. This is a depolarizing blank potential. What is it again? Graded. Yes. Graded potential. Good? Okay. How you feeling? Better? Okay. Starting to get it? Okay. So that's going to lead us to getting to action potentials. We'll get there in just a second. So if the stimulus initiating the graded potential is a chemical, and it binds to and opens a chemical gated or ligand gated, same thing, sodium channel, does it cause depolarization or hyperpolarization? If the stimulus initiating as a chemical and it binds to a chemical gated sodium channel, it causes depolarization. All right, so let's show you guys an animation related to that. This just gives you a visual of the things we've been talking about. All right, so not a dump truck, just a few of
Molecules diffused.
ligands, acetylcholine, binding to ligand-gated sodium channels. Yes? Sodium is moving into the cell, down its electrochemical gradient, blank polarizing the cell. Depolarizing the cell. Yes? Depolarizing the cell. You got a visual for it now, right? So this is a gated ion channel. Okay? All right. So now, just by the way, the initial stimulus doesn't have to be a ligand, but I have a hard time picturing what exists in my retina, which is a freaking photon-gated ion channel. I don't know how to draw that, right? There's also pressure-gated channels and temperature-gated channels, and I don't know how to draw any of those. So I always just picture, okay, the ligand binding to the ligand binding site, and that's what opens or closes the ion channel. But this is any kind of gated channel except voltage, which we're going to meet next. That's a totally different one. That's involved in a different thing. Okay, so sodium is going to move down its electrochemical gradient. You're going to depolarize. So what I want to do now is not just a couple of ions or a couple of molecules of ligand. Now I want to have a dump truck of ligand that is going to work on a neuron. So with this one, although it doesn't show it in the picture, instead of just like 5 or 50 molecules of acetylcholine, I am going to flood that entire cell body with 1,000 molecules of acetylcholine. And what it's going to do is create not a small depolarization, but a massive depolarization. If the depolarization here is massive enough, it can create an electrical change right here at the axon hillock. Okay? So what can happen is I can get the next kind of channel involved. So as sodium floods in, there's a flow of current that's created that's instead of small, like from minus 70 to minus 65, big, from minus 70 all the way up to minus 55. If I hit minus 55 right here, okay, the axon hillock is the first place that I have a new kind of channel called a voltage-gated ion channel, and specifically this one is a voltage-gated sodium channel. What's going to happen is massive voltage changes over there. Even though they dissipate by the time they get here, if they're still big enough, this one will hit what we call threshold. Threshold is the voltage that will open the first voltage-gated ion channel. Threshold is usually minus 55, or average is minus 55. Okay, so do you see that you would need a bigger change over here than minus 55 to get this one to minus 55? Right, because it dissipates as you move over, right? But 1,000 molecules is probably going to do it, right? So I'm going to open the first voltage-gated ion channel. When I open a voltage-gated ion channel, I am no longer in a graded potential, I'm in an action potential. And an action potential is unique to the tissues that everybody has told you forever that are your electrical systems. Yeah? They are electrical because they are the only systems that have voltage-gated ion channels. Yes? And they are, what are your electrical systems? Muscle and nervous, all three kinds of muscle and nervous tissue. Those have voltage-gated ion channels. So as the sodium floods in, the local flow over there was big enough to hit a threshold at your axon hillock of a neuron. And that's called threshold. Threshold stimulus or stronger causes an action potential. So this is what an action potential looks like. It started out right here, but it hit minus 55 in a neuron, which would open massively more ion channels, and I do this, okay? So let's look at this. You ready? Okay, so let's look at what's actually happening right here in an action potential. An action potential is going to be a huge wave of depolarization. So action potentials are always depolarizing. I don't know why none ever evolved that were hyperpolarizing. But what's going to happen is start out the same way that we did before. Cell body, yeah? Dump a dump truck of acetylcholine onto it, and it binds to and opens 1,000 ligand-gated sodium channels simultaneously. So I'm going to get a big wave of depolarization. So big that this one is going to go from minus 70 to minus 55 right here at the axon hillock. What that's going to do is open the first voltage-gated sodium channel. When it opens the first one, it's going to continue to let more sodium in, which is further depolarizing it. But what I want you to understand is these voltage-gated sodium channels are lined up like dominoes all the way down the cell, so that, and they're all set at minus 55 or even closer to 0. As long as you hit minus 55, right? If this one opens at minus 55 and lets more sodium in, can you see that it's going to make pretty damn sure that this one opens and lets more sodium in? This one opens, lets more sodium in. This one, this one, this one, all the way until you get to the end of the cell, okay? That's a fantastic example of what kind of feedback. Yeah, right? In which depolarization by sodium causes the opening of cells that lets more sodium in, which causes the opening of cells that lets more sodium in, causes the opening of cells that lets more sodium in. Why bother? That makes the action potential go from axon hillock to the end of the cell 250 miles an hour. Shoo! Because if you set up your dominoes right, how many dominoes do you have to flick? Just the first one. No, you just have to flick the first one, right? Right? And as long as they're set up properly, right, it goes all the way down without dissipating, right, all the way to the end of the cell. And that's an action potential. Action potentials, now let's reiterate, potential every single cell in the body, right? Pretty similar, every single cell in the body. Graded potentials can happen in every cell in the body anytime you open or close an ion channel. The difference here is that only electrical systems have voltage-gated channels, and they create massive waves of depolarization, but they do it for a purpose. They do it to send a signal with the nervous system or to initiate a contraction with the muscular system, right? And those are the systems that if you get electrocuted, all of those channels are going to open simultaneously, right? And your muscles do that and fry your brain. Okay, so let's look at that. We'll come back to the process in just a second. Let's draw this real quick. Okay, so what we're going to do right here is on the diagram below, sketch the membrane potential recorded in a neuron as it depolarizes to threshold, undergoes an action potential, and then repolarizes to resting membrane potential. So reinforcing terminology. All right. So start at resting membrane potential. What's that? Minus 70. Let's say, not drawn to scale, this is 0, okay? This is minus 55, okay? So you know the damn question. How did you get here? Yeah, so this is leak channels, always present. And then what I'm going to do is I'm going to go, I'm going to draw that a little further up. I'm going to go from here to here, okay? But from there to there, what kind of channel is this right here? Going from resting to threshold. Be specific. Open. Let's specify and say it's ligand gated because we don't want to assume that it's voltage gated because it's not, right? What kind of channel? Sodium. Right? Of course, not one. One of them is not going to get you that far. far, but a bunch of ligand-gated sodium channels simultaneously will get you up. And then here is threshold. So now I'm going to go from here all the way up, usually past 0. Okay, so what kind of channel is this? Voltage gated, so open or close? Open, voltage gated sodium, channels. Good? Okay, now I haven't taught you this yet, but I want to see if you can figure it out. So, we're sending an electrical signal, that's all well and good, but aren't we disturbing homeostasis pretty massively? Okay, so now what we are going to have to do, we're going to have to fix that, or else we're never going to be able to use that neuron to send another signal. Okay, so let's start thinking about how we fixed it. We just actually let a whole bunch of sodium in until maybe we even went past 0. And now I'm at the top. So question for you. How am I going to cause the repolarization that I need? I'm going to have to do 2 things at the top. What are the 2 things? Close sodium, yeah. Sodium and open what? Open potassium. And by the way, those are voltage-gated potassium channels. They just open up here close to 0. They don't open at -55, right? If you make them so that they open, right, well after your sodium has already moved, then they're set properly. So now what's going to happen is I'm going to move down here. They always slightly overshoot -70 just because diffusion rate. It's not really exact. And then it'll go right back up. So what is open right here? Yeah, this is just still open, right? This primarily opens voltage-gated potassium channels. Got it? Okay. So, questions? Or do you want to go through it in your notes and then ask questions? Okay, we're going to go through it in the notes. Okay, so here we go. Action potential. It is an action potential when you are involving the voltage-gated channels. That means action potentials are unique to your electrical tissues. So all cells have resting membrane potentials and graded potentials. Only electrical systems have action potentials and voltage-gated channels. Good? Okay, so this is a huge wave of depolarization that's caused by the opening of sequential voltage-gated sodium channels, and it propagates itself very quickly till the end of the cell. So the process is voltage-gated sodium channels open on the area of the cell membrane that's not the same area that had the ligand-gated channels, but it's got to be close enough that you can actually get it to open. The axon hillock is the important part in a neuron. It's different in muscle cells, but still. And then massive quantities of sodium ions rush in as the voltage-gated channels cause the opening of other voltage-gated channels, right, sort of perpetuating itself. And the action potential moves as a wave of depolarization from the axon hillock to the axon terminals, right? Wave of depolarization all the way down. Each channel opening adds to the depolarization, which further propagates it, which adds to the depolarization, which further propagates it. So it's a great example of positive feedback. But can you understand why I didn't try to teach you this example during the first 2 days of class? Because you would have all dropped, right? And I don't want that to happen for any of us. The electrical change is really dramatic. It goes all the way from -70, it usually overshoots 0, and even for a minute flips the charge so that the cell is positive 30. But it doesn't stay there. It just goes all the way back up. So how about the repolarization? So the repolarization is actually kind of interesting too, because the repolarization, so I want you to think about this for just a second. If the way that you make an action potential is to move massive amounts of sodium inside the cell, right? Okay. I can't use this cell again to send another action potential until I fix what I just did, right? So what I could do, but I don't, is to move an action potential all the way down to the end of the cell, depolarizing the whole thing, and then start right here and repolarize the whole thing. But then there would be a lag time in which I really couldn't use that cell for another action potential. So instead of depolarize and then start repolarizing, I actually chase depolarization with repolarization. So what I do right here, axon hillock, which would be the first voltage-gated sodium channel to open, that one opens, sodium rushes in, which makes sure that this one opens, sodium rushes in. But immediately after this one opens, I close sodium there, open potassium, Then I have to fix the location of the ions, don't I? So I have to do what here? Sodium potassium pump, right? Because everything's in the wrong place after I depolarize and then repolarize. Sodium's in the wrong place, potassium's in the wrong place. If I tried to depolarize again, sodium wouldn't move the right direction. So I close sodium, open potassium, pump them back in the right direction, and then do it here. Open this one, depolarize this spot, close sodium, open potassium, pump them back in the right spot. Here, right? So I'm chasing depolarization with repolarization. So there's very little lag time between one action potential and when I can send the other one, right? Because your nervous system wouldn't do you a damn bit of good if you could only send one action potential, would it? You're like, that was a nice nanosecond to be alive, right? And then nothing, right? So you chase depolarization with repolarization. Is that okay? So chase depolarization with repolarization. So the repolarization, as soon as the neighboring spot depolarizes, the preceding spot repolarizes via this mechanism. Voltage-gated sodium channels close. It stops the depolarization, okay? Then voltage-gated potassium channels briefly open, right? And potassium rushes outside the cell, allows for repolarization. That resets the number, but the ions are in the wrong place, right? And then the sodium-potassium pump has to put the ions back in the original position. Is that okay? Okay, so you already did this, so let me show you the animation. By the way, although it pisses me off, you don't really have to close the sodium before you open the potassium. I just wish it would. Because you can actually open the potassium first and then it'll go, right? And then close the sodium and then it'll start heading down. But the parent in me wants you to put away one toy before you get the other one out. So the order that those two occur in differs from cell to cell, and the animation shows them in the other order, and it pisses me off if there isn't another good animation. I don't know how to make one. So I'll show you guys that. All right, so is that it? Can't remember what that animation is. Voltage-gated ion channels. Oh, there it is. Okay. Ready? Okay, and we're going to pick this up next time. So sodium channel, it's got an open gate and a closed gate, and that's a potassium channel. So this is all after resting and then graded, right? Because what's going to happen is these are going to be caused to be opened by a change in voltage. So they're just going to represent the change in voltage with a zap. So you're going to see, so sodium channels, okay, zap, that was minus 55. So what's going to happen at minus 55 is voltage-gated sodium channel is going to open. And where am I on this graph? I'm moving from right here up, yes? Voltage-gated sodium channel is going to open, okay? And sodium is rushing in. But then, now, look, okay? Now, the sodium is open and the potassium is open. Where I am is at the crest of that hill, right? I'm going to stop the depolarization, not as logically as if I close the sodium first, but it still doesn't matter. And now, come on, you can do it. Now I'm going to close the sodium. Where am I in the graph now? Yeah, I'm heading down, right? Because now it's only potassium that's moving as I'm heading down, okay? And then I have to reset the whole thing before I can have another action potential. So you'll see that it resets the sodium channels. Everybody okay? Okay, so tell me a voltage that might make sense for the voltage that causes the voltage-gated potassium channels to open. Yeah, number. Mm-hmm. 0 to positive 30, anywhere along there it happens, right? Definitely not negative 55, right? So it has to be that other direction, right? And a similar voltage would be responsible for closing the sodium channels, right? Okay. Either one can happen first or the other one can happen. So one might be set at minus, so one might be set at 0, one might be set at positive 20, right? And then that would be what order they open and close in, or it could be the other order. Either way, it's going to make you go back down. Okay? All right, so we are stopping there. That's all the hard stuff. here's my challenge to you, is that you have to study this before you sleep, because you will lose all the benefit of having understood it today, okay? And I did move your test, so it's not, you're gonna have a week between when you finish this material and the next time, but it requires a lot of you. You actually have to sort of be honest with yourself and figure out where you get it. So I will put this up as soon as possible today.